All right, so thanks for the introduction. This is, I'm going to talk about our paper called Instance-Dependent Regret Bounds for Dueling Bandits. This is joint work with Akshay, Zohar, and Rob. And so the first question is, what are dueling bandits? And so you have k actions, or arms. And so in each time step, the procedure is that the algorithm gets to choose two arms, R and C, for row and column. And a duel is conducted between the two actions. So for instance, these could be two rankings, which are interleaved together. And you get one of them as the winner of the match. And the goal is to converge to the optimal play for both row and column players. And I'll get to what optimal play means in the next slide. But let's just fix some notation for now, which is this preference matrix P, which is whose entry ij is the probability that action I beats action J minus a half. And the reason for the minus a half is because we want this to be a symmetric game. So we want the matrix to be the matrix of a symmetric game. So that's preference matrix P. And the question is, what is optimal play? It's just a distribution W. By distribution, I mean a probability distribution W on the set of actions, such that if you choose the row action, IID from this distribution, and if you pick the column action to be a fixed action, then this W would beat the column player on average. So that's what. Can you hear me? Yes. So that's this W, and let's look at some examples. Thou shalt give examples. So the first and simplest example is the case of this Condorcet winner, where you have a single arm that beats everyone else, and therefore you should put all of your weight on that one action. So that's the simplest case. Next one is rock paper scissors, where because you have the game is invariant under permutations of the actions. You should put equal weight on all the different actions. So, and you can combine these two by taking rock paper scissors or just any game and add other actions, all of which lose to all of the previous to rock paper and scissors. So, the main quantity for us is this quantity S, which I call the support size, which is number of arms or number of actions that have non-zero weight according to the optimal policy, and or the optimal or mixed strategy. And the important fact is that this support size is very often much smaller than the total number of actions. So this is just something that comes up both in experimentally in practice, and there are arguments for why this should be the case. And so there's this, going back to the previous work. I mean, there's this dichotomy. On the one hand, people assume that the support size is equal to 1, and then they get O of log T regret bounds. And then there's the case when you just don't assume that, and then you jump to O of square root of KT. And so we try to improve on that. We try to bridge this gap. 5 minutes or 5 seconds? Okay, 5 minutes. Okay, then I have plenty of time. Okay, let's take it slow then. All right, because this is the last slide, so you guys had better ask some questions over here, I'm telling you. But anyway, so so let me just take it slow and explain to you the algorithm. So you just put essentially two no regret algorithms on the row player and the column player. Let's say x3.p. And then what you do is you maintain a confidence interval or a confidence region around your preference matrix or your symmetric game matrix or whatever you want to call it. And then you start eliminating arms as soon as you realize that there is no other matrix in your confidence region that has this arm in its supports anywhere, right? I mean, so once that happens, then you can just eliminate that arm and go your merry way. And then once you do this, you get something that is the minimum of what you get from these no regret algorithms, which is square root KT and the no regret algorithm on the smaller set, which is square root of SC. So because now you've eliminated a pile of arms, and so now you can converge a bit faster. And the main challenge, I just want to say, is that it's computational. So it's that confidence region. So you can put a confidence region, like figuring out when an arm is not in the support of the von Neumann winner of any matrix inside your confidence region is not a trivial problem, and so we have, we get around that somehow. So, and I'm not going to tell you how. So this is, yeah.